Alright, welcome everybody to week 10 or something, day 1. So the classes competency exam was due today, as was the linked list one. Let's see, I think it was due today. Let me just double check that, make sure I'm not giving out the answers. Classes, competency exam, take 3. No, that was due 5 days ago. Okay, so let's talk about that first, and then the linked list one was due 3 minutes ago, so we'll go over that one too. So we will be doing a take 4 for the classes competency exam. Again, you will need to make an appointment with Muya, and he will give you the password for it, and that will be how that is. So let's look at the take 3 competency exam. Almost nobody got this one right, which is, if you're going to make a class that's going to allocate memory, which of these functions should you make? This is called the rule of 3, and in the rule of 3 there are 4 functions that it applies to, of course. The rule of 3 is, if you have a constructor that's allocating memory, you need to make these 3 things. That's the rule of 3. And so a lot of people left off the constructor. So what is a constructor? What is a copy constructor? What is a destructor? What is an assignment operator? Mulia will go over that again with you guys for the next one. So is it proper class designed to have all of your member variables be public? Literally 100% of people got that, so cool. 100% of people got, in general, your get methods should be const methods, and so almost everybody failed the first question. Everybody got the second and third ones right, and then the tiebreaker was if you could write a class within the 20-minute timeline. And so it's not hard, but at the same time, like, if you're not with that ability to write classes, you need to practice it. You need to be able to spit out a simple class, and I mean, 20 minutes is, you know, it's a fair bit of time, right? So timer, begin. Okay, wait, no, that's a 1 minute timer. Stop. I want the other one. I want a stopwatch. Start. All right. Vim circle.cc. All right. Actually, we don't need to do any of this because we are just doing a class. So class circle, and this has a point, double xy, which are the point of the origin of the circle, and then you have a radius like that. Then you have a public section. Public section needs to have a constructor in it, and so we'll initialize x to be 0, y to be 0, and radius to be 0, or we can just do it this way, which is even faster, like that. There's your constructor, and then you can have a another constructor, or you can do the clever one, double new x defaults to 0, double new y equals 0, double new radius equals 0. That'll give you all 3 constructors, and then you can just initialize them using the initialization list, like that. So there's your constructors. Then you need get and set methods. So we're going to have double get x, which will return x, and if we're doing this properly, we should have here. Does it not like this? Let's get comma. Okay. Get x, get y, get z, or get radius. That. There's your get methods. Your set methods will be void set x, taking in double new x. X is equal to new x. YYPP. Change it to be a y. 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 S radius. Dot. 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 Somebody's unmuted again. So there's your set methods. There's your get methods. There's your set methods. And then finally, the one thing you need is the within function. And a lot of people screwed this up. They're taking in strings and like passing in all this stuff. The definition of it was very straightforward, which is it takes in a new x and a new y. We'll call this other x and double other y. That's it. If you took in any other parameters, if you returned any other thing, your code was wrong. It takes in a point and you return it true or false. And so we just take the distance of that point to our center point. So that would be hypot part of the CMath library. Hypot gives you the distance of x minus other x, y minus other y. So that tells you the distance. The other point is from your radius, and so you're just going to return. Oops. What the hell is going on here? Return hypot. There we go. Return. If radius is greater than or equal to the distance of the other point, then that should be other y. There we go. And that's it. So if the distance to the other point is bigger than a radius, it's outside of the circle. If it's smaller than a radius, it's inside the circle. And that is a circle class. And that took 4 minutes to make. Okay. So you don't have to be at the 4-minute mark, but you got 20 minutes to do it. So we'll do another competency exam for you guys on that, and it'll be on the same level of complexity. Make a simple class with a simple member function on it. Some people, like one student, screwed up like one of the minor types or something. I was fairly generous with it, but if you don't understand how member variables work and things like that, you're not going to get it right. And so you need to practice this. This is the most important concept in this entire class, is the class concept, right? So, and then for the linked list competency exam, so please take it a 4th time, make another appointment with Muya, go over how to make a class, and because if you don't, you're literally going to potato the entire rest of your computer science career. You have to know how to make a class. It is 100% required. You have to understand what's happening with a member variable, how a constructor works, the rule of 3. It's mandatory for the rest of your career to know that stuff. Okay, so for the linked list competency exam, we have not great results on this one as well. So let's go through this. This function here looks like it is freeing all of the nodes in the linked list, and it probably is. But this is a use after free bug. It is deleting temp, and then it is saying temp equals 10 points to next. It's not allowed. You cannot say temp equals 10 points to next after you've deleted temp, right? You have to remember how a for loop works. You start off, this line here takes place before the loop. This takes place to see if the loop runs, and then this takes place at the end of the loop. So after it deletes temp, then it is moving to the next node in the linked list, which you cannot do. It is a use after free. It is definitely not copying from one list to another. That's no. There's no. Yeah. Okay. In plain English, what is this code doing? So about 50-50 on this one. It is printing out all the nodes in the linked list. Nope. This one is also. This one is also buggy. Okay. So there is no terminating condition here. This is going to print head. It's going to print the data in head. It doesn't check. The first thing you should always do with a pointer is check to see if the pointer is null. That's guaranteed, 100%. First thing you should always do. If you have a function that takes a pointer, you need to see if that pointer is null. It's not in here. Not in there anywhere. And that's why I put that question in here. So it will print out heads data, then it moves to the next node of the list, then it prints out that data, moves to the next. There's no terminating condition here. This is an infinite loop. It's a recursive call that has no terminator. It is guaranteed to cycle. Okay. All right. What operations are lists faster than vectors at? Check all that apply. Deleting from the front is faster on a list than a vector. On a list, deleting from the front is order 1. Deleting from the front of a vector is order n. If you delete from the front of a vector, it has to move all of the elements in the vector forward 1 element. So if you have a billion people in the vector, if you delete the first element of the vector, you have to move everything forward 1 element. Okay. Inserting from the front, same thing. You can insert at the front of a list in order 1 time. Deleting from the inserting at the front of a vector is order n as well. Printing out all the elements in the data structure is the same speed. It's order n for both of them. So you have to iterate through a linked list. You have to iterate through the vector. There's no faster way of doing it. It's order n. And then deleting from the middle is also faster for a list than a vector. If you delete from the middle of a linked list, that is order 1. If you delete from the middle of a vector, it is order n. And it's order 1 if you have a pointer to that spot you're going to delete it. If you don't have a pointer to that spot and you have to find it, then you got to iterate to the middle, and that becomes order n. But assuming you have a pointer there, it is order 1. And this question here is really, so these things here are testing your knowledge of being able to work with pointers, right? And being able to understand when you're going to segfault and when it's going to work right. That's what these two things are testing here. This one is the big concept for this class, which is when should I use what data structure? When should I use a vector? When should I use a linked list? When should I use a queue or stack, which technically you can do with a list or a vector? When should I use a binary search tree? Okay, that is the big, conceptual thing that you need to walk away from this class with. I should be able to give you a scenario of like, these are the operations I'm going to be doing a lot. I'm going to be inserting at the end a lot. I'm never inserting in the beginning, All right, let's use a vector then, I guess, Okay. 3 out of 4 is a pass. 3 out of 4 is a pass. And I've graded all of the competency exams for the classes. I've not, I graded all the linked list ones as of, I don't know, a day or two ago, but obviously most of them came in before the deadline, so I have a backlog of those things to go through. Write a copy constructor for the linked list class. We've been using in class. We'll do a deep copy. Yeah, so let's do that. So then linked list dot h class list. Right, so given the signature for a copy constructor looks like this. Every constructor has a function name equal to the name of the class, right? With no return type. That's what makes something a constructor. Has no return type, just has the name of the class. Okay. So it's going to take in a const list by reference named other. And what we're going to do is we've got our node pointer head or whatever. You don't have to write all that stuff. All you have to do is write just this one function. So we will just, like, assuming we have got like a pushback function, we'll just say node pointer temp equals other dot head. So we'll get the head pointer out of the other guy. And then we will say while temp. Pushback temp points to data. So we will copy the data from temp into the end of our list. And then temp equals temp points to next. And so that is a copy constructor. That's it. So what it's going to do is, and I can turn this into a for loop if I wanted, for node pointer temp equals other dot head, as long as temp is not null. Equals temp points to next. There. That's it. That's all you had to write. 2 lines of code. So create a pointer to the other guy's head, and what we're going to do is we're going to copy. So this is called a deep copy. You iterate through the entire list on the other side, copying all the data elements into your own list. Yeah. A shallow copy means I just set my head to point to their head, and now the 2 lists are sharing the same chunks of memory, and that's really bad because if you delete from one list, it'll delete from the other list. That's not what you want. If you're going to copy a list, you need to do a deep copy and go through every node in their list and add them to your list. That's it. That's all you do. Yours is not graded yet. Yeah, I have not graded all the competency exams yet. You made sure to go heavy on deep and shallow copy during the review. Cool. Yeah, so Mulia's review is up on YouTube or something. But also that was for the classes one. So yeah, that's it. So this one had a lot less coding than the classes one. But the reason why the classes one has coding is because you need to get used to generating that boilerplate for gets and sets and constructors, which is really annoying. And I realize that. Like, that's one of the things that I really like about C# is you can just be like, get, set, or however, and it just makes the getters and setters for you, which is really nice. Especially if you're in a time crunch. When is the take 2 for the linked list? I'll post when that's available. I'm going to try and have take 4 for the classes competency exam up first, and then I'll do a take 2 on the linked list one. All right, so we're going to continue our discussion of binary search trees today. If you guys have any other questions about classes, proper class design, having an interface, mute. You can see all the people that come in late because they're not muted. Any questions about class design or linked lists? What newing something is? You need to just write code for it. Is the real answer here. You need to write enough code that you get good at these things. Okay. Yeah, working with pointers is annoying, and you just kind of have to get practice doing it. All right, so fat thumb the first question when you scroll down and put it in a different answer. Yeah, sorry. All right, so with a tree, every node in the tree is going to contain some sort of data of type T. Remember, we're templating this bad boy here. And then every node is going to have a left pointer and a right pointer. And they'll default to be null. That's how you know you've hit the bottom of the tree. The bottom of a tree is a leaf. Right? So head is null if the tree is empty, otherwise it points to the root. Duplicates allowed. Another class invariant is, of course, all elements in the left subtree are less than the current. All elements in the right subtree are greater than the current node's data. You guys understand? So that is the rule for a binary search tree. Okay. These are the rules. If the tree is empty, if there's nothing in it, head is null. Otherwise, it points at the root of the tree. And I should probably just call it root, but whatever. Gone too far at this point. No duplicates are allowed. So if you try inserting a duplicate, it just bails out. And then everybody in the left tree is smaller than me. Everybody in the right tree is bigger than me. Are we doing delete today? Maybe. It's the hardest part. So what else do we need to do? We've done insert. We've done search. What else could we do? We could do a copy constructor. Oh, we need to do a destructor, don't we? Right? Because our thing is allocating memory. We've got a new, we've got no delete. Right? Is pop need delete? I don't know what that means. There's no pop in a binary search tree. Binary search trees have insert, search, and delete. And there's no push or pop because there's no order. Right? In a list or a vector, there's an order. Like if you insert 1, 2, 3, then it's inserted in the order of 1, 2, 3. For binary search tree, there's no ordering of the thing. It doesn't remember. It does not remember what order you put the data in. Binary search trees lose that data. So sometimes that's one of the reasons why you have to use a vector. It's like, you need to preserve the order that things came in. If you're making a network buffer, data's coming in from the network, you can't use a binary search tree on it because it'll like all the packets will come in the wrong order, and that would be bad. That'd be bad. Yeah, don't apologize. It's just it's a good question. All right, so a destructor. We do a destructor. All right. Let's see if we can do this. Actually, let's see. G. Let's see, compile. Syntax error. AST broken. All right. Alias. Do not have address sanitizer turned on. All right, g++ -f sanitize equals address bst.cc declaration. What happened here at line 19? Oh yeah, that's funny. That's funny. The A style, the thing that cleans up the code, it does not work with C++ 20. That's interesting. Okay. 20. So it actually reformatted the spaceship operator into two different comparison operators. That's hilarious. Okay. So it actually broke the code. All right. So we got a memory leak. Okay. So we've got a memory leak. One object was allocated here. 3 objects were allocated here. 2 objects were allocated here. So we've got news on 56, news on 71, news on 65. So there's 3 different places where we are allocating nodes in our battleship tree or whatever. Best sentence taken out of context. Which one? Oh, yeah. Tell the parents to kill their children. Yeah. So we got leaks going on here. We need to fix that. Okay. So how should we do this? So again, the battleship class doesn't know anything about it being put into a binary search tree. A lot of students will try to put like a destructor here. No. This class does not need a destructor. The name will clean itself up. The name class has the string class name has its own destructor, so we don't need to worry about that. We're basically cool. So the battleship class is just a string and a number and some comparison operators. It doesn't know anything about a left child or right child. A lot of people try merging those two things together, which is bad practice. A binary search tree should hold some type of data, and that type of data should not care if it's in a vector or a binary search tree and things like that. You may need to have some operators on it to enable it to work in a binary search tree, but these operators you would use anyway if you want to sort. Like if you wanted to sort a vector of battleships, you sort a vector of battleships using the less than operator, right? By default. And so this magic thing here, the spaceship operator, generates all 6 of the comparison operators for you, and so including less than. So this is C++ 20 magic right here. But if you didn't want to use C++ 20, then you would do the less than operator like this, right? The less than operator is the most important operator. All right, I know we've talked about this before, but it's like if you make a class that just holds data, like a person and it's got a name and a phone number and a social security number, the single most important operator to put on it is the less than operator. Not less than or equals, not greater than, less than. Because everything in C++ that cares about comparisons uses less than. Okay? And so if you're going to write only one operator, it would be less than. And then if you're going to write 2, I would do double equals as well. Okay. So between this one and this one, you usually can work with any data structure, but this spaceship operator is nice because it'll actually make all of the comparison operations for you. So yeah, I would probably go about it this way now, but that way works just fine too. And so you could just do that one line of code, operator less than with that one highlighted line of code there, and you're good to go. Okay. Do you figure out why double equals is not working? No, I didn't look at it. If anybody wants to try and figure that out, that'd be cool. Does using head instead of root change anything? No, it's just a name. I should call it root, but whatever. It doesn't matter because it's not exposed to main. Main doesn't know anything about head or root. It's private. See, right there, it's node pointer head equals null pointer. It's in the private section. All right, so we got insert. Okay, so we need to do a deleter. So we got our cool constructor here. Does nothing. So what are we going to do? We're going to do a destructor. All right. So a destructor looks like this: tilde with a tree, tilde with class name is a destructor. So when the tree goes out of scope, we need to delete all of the elements in the tree. Okay. So how do we do this? We need to delete everybody in the left subtree. Delete everybody in the right subtree. And then delete me. Let's try that.
Just delete me and that's it. Because in the node class, you can then write a destructor for that deletes the left and right subtrees.
Yes, that's a good point. Yes, correct. Delete head is what we want to do. Yes. And then the node, we will have a destructor here. Delete left. Delete right. I can't delete this. Because delete this, we'll call the destructor, right? Let's see.
I don't think you need to delete this, do you?
Nope, you don't. Yeah. It's an infinite loop if you delete this. I only put that in there to show you guys that you don't need to delete this. Okay, so you might be wondering, how is this not an infinite loop? Right? Right. No, that was not the question I was expecting, but okay. So that's what happens when you give a lecture after sea shanty night. All right, Ephraim, you are now muted. Yep. You can always tell who comes in late because they're not muted. Okay. So why do we not need to check to see if left is null first? We could do this if we wanted. Say if left, delete left. If right, delete right. We could do that if we want. Same thing. As it turns out, if you delete a null pointer, it doesn't do anything. So you can actually write a very quick and easy destructor that way. And so if left is a null pointer, it doesn't do anything. If it exists, then it deletes it and then recursively calls its destructors as well. So that frees up all the memory. Okay. So for the destructor for the tree, all the tree needs to do is delete the root of the tree. You know what, I'm going to go and redo it now. So head, so is now going to be root 4s root, n to find the next one, dot to repeat the last substitution, next dot, next dot, next dot, next dot, next dot, and that's it. Now you might be like, why don't you use search and replace in Vim? Well, I never do a global search and replace, almost ever. And there is an interactive one, which basically does the same thing as what I did right there, but it's actually faster for me to just hit n and dot a bunch of times. Because what if I had out here, you know, a battleship called head? Then the battleship head would now be called the battleship root, which is not what I want, right? So I'm always very, very cautious when doing a global search and replace on my code. So I typically do manual search and replace. If you're using Visual Studio, they have an intelligent rename function. It's actually one of the nicest things. You just right click on it and choose rename variable, and then it finds every instance of that name of that variable head, and it changes it to root. It's very nice. Very nice. Okay, so there we go. So we got the battleship A, C, head, and main. So you can see that B doesn't exist anymore. We got head now. Okay, so that was a destructor. You guys have any questions about the destructor? So it just deletes the root because the root is nude, and then the root will call the destructor on each of the nodes, and they'll delete each of their kids if they exist. So it's pretty simple, pretty straightforward destructor. 2 lines of code there, 1 line of code there. All of these things are really simple, but at the same time, students have a really hard time with linked lists and binary search trees. Like, do you guys agree? Like, working with stacks and queues were like pretty damn easy, but like and vectors are pretty easy. But like the pointer stuff kind of hurts your brain, you know, a little bit. If you're like me, at least. I'm hearing chords. So the pointers that get confusing, yeah. Yeah, a pointer, yeah. Yeah, when you knew something, like it really helps to understand what's happening when you knew something. So when you knew something, all new does is it finds an available block of RAM equal to the size of a node. A node here would be however big the T is. In this case, a battleship is probably 32 bytes, just off the top of my head. And so it's 32 bytes, and then the pointer's 8 bytes, and that's 8 bytes, and so we're talking 1650. Probably, yeah, somewhere on the order of 50 bytes or so. Alignment makes it a little more complicated to figure out in your head. But yeah, around 50 bytes. And so when you say new node, the new system, there's a whole, that's a very complicated thing. What new does is it finds 50 bytes of RAM that are open. And it says, okay, that is now root. Or what it does, the new system actually doesn't know anything about it. It just knows I need to find 50 bytes of memory. And it returns a pointer to the beginning of those 50 bytes of memory. And so root holds just an integer in it that holds the beginning of that 50 bytes of memory. It's like an array almost. So it's the first element in the array. Classes are actually arrays, basically, behind the scenes. And so root just holds the beginning of those 50 bytes of memory. That's it. And the bit here, it just initializes the root's data to be new data. It calls the constructor. So that's all new does. Roots left and right pointers are set to null. Why? Because we've got a constructor on them. This generates a constructor for you if one does not exist. This didn't used to work, by the way. In C++, 98 and earlier, you cannot do that. You had to make a constructor every time. So, we've got a root that is pointing to some 50 bytes of memory, and it's left kid and right kid are null. And then if we go into insert, if we're going to insert something, the reason why I keep repeating this is because you just need to keep going over it over and over again in your head until it kind of sinks in. 3, 15, 21. So after we call that first line of code there, new is going to return some block of memory. Let's say this is 50 bytes big. And so root is going to be pointing at the beginning of those 50 bytes, and it's going to have a data holding a battleship, and it's going to have a left, it's going to have a right. And these are both set to null. Now let's say I insert, let's say I'm just holding integers to make life easier on me. So let's say we inserted 10. Okay. Now let's say we're going to insert 5. So what happens is here, root is not null. So we come down here. We set current to equal root. So what does that mean? So it's a pointer. Current is a pointer. And a pointer is just an integer. So current is just set to be equal to the integer value of root. Root is just some memory address. It's some place in RAM where this data exists. And so it's doing an integer copy. It's saying it's like when you say integer x equals y, it just copies the value of y and x. And so whatever integer is in root is now in current. So currents now hold the memory address of this block of memory here. And then we say, well, is current equal to 0? It's not. It's pointing at some address in RAM. So if current points to data equals new data, we're inserting 5. 5 does not match the root's value, so we continue on. If current points to left equals null pointer. So if current points to left equals null pointer. So current points to left is that guy right there. And that guy right there is currently set to null. So current points to left equals null pointer, 0, which is null pointer. Cool, we have found an open spot. So what happens is this pointer is going to be set to, we call new again. So we call new again. New is going to allocate another 50 bytes of memory and return a memory address. And so, maybe just visualizing it, the memory subsystem doesn't have to pick a block of memory anywhere near the other one. But that memory address, whatever that is, the start of that 50 bytes, that gets saved into the left pointer. And so normally when we draw a binary search tree, we don't draw it based on where it is in RAM. We draw it conceptually. So the left pointer is now pointing at some chunk of memory. It holds the value of 5. Its left and its right pointers are both set to null. And now let's say we insert 7. Okay, from the top, inserting 7. Current equals root. So current is pointing at root. Does 7 equal root's data? True or false? What do you guys think? So if we're inserting, here's our tree. We're inserting 7. Does 7 match? Does 7 match the data held in root? It doesn't. Is 7 less than 10 or is it greater than 10? Leader? Edgerlin trying to split the difference. Leader? Yeah, so 7 is less than 10. So what happens here is if 7 is less than 10, then we check to see is root's left null? No. So if root's less is not null, then we will say current equals current points to left. So current equals current points to left. So current now points at these 50 bytes of RAM here. Okay. So it is now pointing at that person we inserted the last time. So that those 50 bytes of RAM, wherever they are, current now holds that number in its variable. And We come back up to the top of the loop. Is current null? Technically, we could probably do this with a while true. I don't think there's any need for while current, but I always check to see if, like, it's just a habit of mine. Like, I don't like subfaulting. Okay. So current is not null currently. Current is currently pointing here. So we continue onwards. Does 7 match 5? Is 7 and 5 the same number? No. Okay. Is it less than? Is 7 less than 5? No. So we come down here and we say if the right pointer is null, which it is, then the right pointer is set to be new node passing in 7. So the right pointer is this guy here, and its right pointer new is going to allocate another 50 bytes of memory. It's going to save 7 into the data. Well, it's not 50 now, it's an integer. So it'd be 4 bytes for the integer and 16 bytes for the like if we're just holding ints and not battleships, this makes this a little smaller. It'd be due to alignment, it's probably going to be 24 bytes. 24 bytes. This is 24 bytes. This is 24 bytes. So it's going to allocate 24 bytes there, and his left pointer is 0 and his right pointer is 0. Okay. Does that help kind of understand what's going on with the binary search tree? Like, all these pointers they're just some number, right? Like, when new allocated 24 bytes of memory, this might be at memory address, I don't know, 9,000. And so this guy's pointer is just holds the number 9,000. And this guy, when he was newed, he might have been allocated at memory address F F F A O O O O. And so the pointer here would be holding F F F. It's really too small to write. A O O O. Yep. So, or that's a little bit too annoying to work with. Just make this memory address 500. Okay, that'll be easier. So the left pointer of root holds the number 500. All pointers are just numbers. And that's why when you copy one pointer to another pointer, it's not doing anything magical. It's literally it's as if you had said integer x equals integer y. It just copies the number over. That's all that's happening. There's no magic that takes place with that. Okay. Left isn't previous is to the left, right isn't next to the right. Yeah. So yep. So that's all that's going on there. You can print the pointers out if you want, and it'll give you some memory address that won't mean anything to you. You can look at it. All right. Okay. So now we need to do. We've done insert. Have we done search yet? Have we done search? We've done print. We haven't done search. Okay. So let's do search. So let's do search. So if I want to search to see if the number 7 is in that tree, what should the return type on search be? What should the function signature look like? Bool. Yeah. Book. Bool. Search. Find. Search. Search. Find. Find. And we're going to be searching for a t, const t by reference, called key, I guess. I don't know. Okay. Lube. So we want to return true if the needle in the haystack is found. If the key is found, we return true. If it's not in the tree, we return false. Okay. So what is the firstest thing we should always do when working with pointers? What is the firstest thing we should always do when working with pointers? Very good. So, if the head is null, if there's no elements in the tree, do we return true or do we return false? What do you guys think? Couldn't fool any of you guys. Yeah, it should be false. I was going to see if any of you guys would just agree that it was true because the professor had written it. Oh, it's not head anymore. Dang it. I changed the name of it to root. Hoisted by my own petard. Yes, if the root is null, I don't know why I keep calling it head. It's root now, as it should be. If the root of the tree is null, then we return false. There's nothing in there. You can't find it. You're searching for the number 42. Tree's empty. Sorry, man. It's not in there. All right. F in the chat. Yeah. All right. So, all right. Cool. All right. Neat. All right. So let's do a while true. Like I said, this could be a while true also. Technically, you don't need it to be. Yeah. Okay, while true. So what's the first thing we should check for? So we called find. We're searching for the number, I don't know, 5. All right, so the key that we're searching for is 5. What's the first thing we should do? We're here currently. So we got a pointer or something. Current, we should make a current pointer maybe. Yeah, probably a good idea. Okay, so node pointer current equals root. Probably the first thing we should do. So that pointer is just going to traverse down the tree and it's going to go to the left and go to the right and whatever. For a search tree of names, what should the root be? Just the first name that gets passed in? Sure. Yep. Okay, so node pointer current equals root. All right, so what's the first thing we check? Yes, very good. Biddinghoven. First thing we should check to see is, did we get a match? So if we were searching for the number 10, the first thing we should do is see if, you know, the node we're currently at is 10. It's, this extra line here is bugging me. There we go. So did we get a match? If we got a match, what do we do? If current points to data equals key, what do we do? Return true. We're done. If not, then that means it's either going to be less than or greater than, right? So if key is less than current points to data, so if the number we're looking for is to the left, we say actually, yeah, let's do it this way. If key is to the left, then current is equal to current points to left. Else, current equals current points to right. Do you see how I made use of just the less than here? Same thing up here. I only use the less than operator. And that's because that's what people expect. When you make a class, if you want your class to work inside of a binary search tree, if you want your class to be able to be sorted, the only operator that is ever required of you is the less than operator. And that's why I used less than here rather than greater than. Right? I always use the less than operator. So all right. So there is our find function. We're done. So if the key we're looking for is less than the current data, then current equals current points left. So if we're searching for 5 and the current value is 10, 5 is less than 10, therefore current equals current points to left, which does that. Current equals current points left. It was pointing here, current points to left is 500, so current is now 500. Current equals current points left, boom. And then the next iteration around, 5 matches the key, it returns true. If we were, however, searching for -5, then what would happen is current equals current points to left again. So current would be pointing to null. And then that while current would be false. So it'll return false. So pretty easy. A few lines of code. Is there a different tree too? You keep saying binary tree, which mean might either be tree base 3. Yeah. And there's even different kinds of binary trees as well. This is something called a binary search tree. That's why I call it a BST for short. When people say binary tree, a lot of times they mean binary search tree. I sometimes use that myself because it's shorter to say than a binary search tree. So people will use binary tree and binary search tree kind of interchangeably. However, there are many different kinds of binary trees, and there are many different kinds of there's quad trees and oct trees and things like that. What are the other kinds of binary trees? Great question. So let's say that you let's say that you're taking IS50B, and so there are you got this giant world. It's like the world of Fortnite. I don't know if kids still play Fortnite these days. I never have. I'm too cool for Fortnite. I play cool games like Valheim that aren't trendy at all. It's a little indie game. You've probably never heard of it. So so let's say you've got this massive world. It's like 10 kilometers on the side or whatever, you know. And let's say that you want to be able to find what is here at this point here, at point 5,000 across and 10,000 down. What is here? Is it solid? Is it liquid? Is it air? What is it? Let's just say a 2D world for now, right? Little indie game that each dev made $16 million off of. Yeah, it's pretty good when you're a team of 5, you know. Sell 5 million copies at $20 each. It's $100 million. Valve takes its cut. Yeah, 60 million sounds about right to me. Yeah, it's pretty good. So, you could just have a list. You know, you could have a vector. You could have a vector of like literally every object in this world. So let's say this world is populated by squares and triangles and circles. There's just stuff all over this world, and there's thousands and millions of objects within this world. And maybe this is a lake here. Let's make it blue. Let's make it a lake. There we go. And so the coder gives a command, tell me what is at this point here. You could do this using a vector. For every shape within this giant world, check to see if that point is within the shape. Pretty easy to do, you know. Rectangles are pretty easy to find out if something's within it, right? It's, you know, in between the x and the y minimum and maximum, right? And to find out if it's within a circle, we just did that earlier in the class, right? So to find out if a point is within a circle, you know what the radius of the circle is, right? So you take the distance to the point, and if the distance to the point is smaller than the distance of the radius, then it's within the circle. Pretty easy. But if you've got a million objects inside the world, this is incredibly slow. And so you're asking what other kinds of binary trees are there? I'll show you. So one way you can do it is with what's called a quad tree. And so a quad tree divides the world into quarters, yoink, yoink, and then recursively subdivides, yoink, 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 yoink. Okay, and so in order to find out what's at a point, you just recurse down the subtree. And so when you insert the square here, it's going to have children added to this tree here and this tree here. Okay, and and so if you want to find out what's at that point, you just say, all right, is that point north? Is it in the northwest corner, southwest corner, southeast corner, northeast corner? Okay, it's in the northwest corner, and you recurse down the tree that way until you find, oh, that's within the lake. Cool. Return lake. So that would be very commonly used. Use quad trees for 2D and use oct trees for 3D. Very common. Super common data structure. So what about another use of a binary tree? Well, so there is something called a binary space partition, a BSP, as you will. And so what the binary space partition does, it takes a world like this and it divides it into a left subtree into a right subtree. So everything in the left subtree is to the left of this line, right? So you can imagine a line coming up here. So everything in the left subtree is to the left of this line, and everything in the right subtree is to the right of the line. And so this is a binary tree. It's not a binary search tree, it's a binary tree. And then you will cast a line out this way here. And so everything to the left is in the left subtree, everything to the right is in the right subtree. There's only one object in each of these things, so we're done. So we'll have a binary search tree, and this will have like the line basically in it, and the line in it. And then it's got the object, what is that? We got the lake so it's going to have like the square, and it's going to have the lake in it. And then when you want to say, hey, what's at this position here? What's there? You take the cross product of, won't mean anything to you until you take linear algebra, I guess, or game development. But you take the cross product of this vector here and this line that you use to divide the tree. And the cross product will tell you, is it to the left or is it to the right? Simple. The cross product is just x1, y2 minus x2, y1. That's all it is. So you've got, x1, y1 here, x2, y2 here. So you take the cross product of those two things. If the number is positive, it's to the left. If it's negative, it's to the right. Easy peasy. So, or vice versa. It depends which one's the first vector, which one's the second vector. But so okay, it's to the left. Neat. Now we do it again. So now we come to the left subtree, this line here, and we say, is the cross product of this vector and this vector positive or negative? It's negative. Cool. It's to the right, and then you recurse into the right subtree, and then there's only one object left in the right subtree. And so you just check to see whether that point is within the box there. It is. Cool. Return. It's within the lake. And that's how video games work. These are called spatial sorting data structures, things like that. How do you hold the map of a video game? Because they're very big, right? How do you hold them so that you can find things very quickly? When you shoot a gun, like let's say you've got a person here, and they shoot a gun in this direction, right? How do you know what you hit? Shoot a gun in this direction. How do you know what you hit? You got to be able to do that quickly, right? So, and so, yeah, you draw a line until you hit the edge here, then you go into the other, branch of the binary search partition, and see if you hit a box there. If not, then you go into the next one, and So skill-based matchmaking is terrible. Yeah, it's not necessarily that it's terrible. It's just that it's terrible. Yeah, the ELO system was designed for chess, and they adapted it for MMR, for I think League of Legends and things like that. But basically, Matrix and 50A. Yeah, we talk about matrix math and vectors and matrices and dot products and cross products. It's part of the class. So. But there's two big problems with it. First of all, people will smurf, so they will deliberately tank their scores so that they can get easier matches. Or grandmasters will join in and have an ELO rating of 1,000 and just blow all of their competitors out of the way. The other problem is, like, what if there's not enough people playing, right? So let's say you're with your group of friends and you all suck, and the only other people are 4 grandmasters. Is it better to pair the newbies with the grandmasters so they get a game, or is it better to just have them wait and wait and wait and wait for a game that doesn't play? And so if you're a game developer, you don't want people being like, no, there's no games, quit out, because then your game dies. And so they will throw you into a game with the grandmasters a lot of the times, just so that you could be playing. I dropped COD, and I'm thankful I did. They don't care about optimizing anymore. Yeah. Call of Duty has never been a well-optimized game, like as far as I can tell. Or are they called Smurfs because they pretend to be really small? As far as I know. It's called smurfing when you... what? You can prove yourself without compromising the statistics in the main account, without worrying about your record. I don't know where it came from. I imagine it's because you're pretending to be smaller than you actually are. The world's best chess player does it, by the way. So he trolls people on online chess. He goes by Dr. Drunkenstein, or now he's Dr. Soberstein, I think. So Magnus Carlsen, the world-class champion, Dr. Drunkenstein's reign of terror. So he's literally the best chess player in the world. And so he'll just go onto online chess forums under Dr. Drunkenstein, or now Dr. Soberstein, and just obliterate people, you know. And so there's these online streaming matches of like grandmasters are streaming their chess games, and this guy's just obliterating them, and they're just like, just like not even thinking about the moves, just playing, you know. And that's usually a sign it's not even like a a computer playing you, because you know if you're cheating by having a computer play, you have to make their move and then wait for the computer to think about it and then enter the computer's move into yours. He was just like whatever, and just dominates this chess grandmaster. Yeah, it's freaking hilarious, dude. Okay, so I don't know how we got on that, but there we go. Yeah. So, so that would be another example of a binary tree. Okay, but it's not a binary search tree like we're talking about. Are you guys with me on this? So this is a pretty classic data structure in trying to, you know, visually sort where things are in the world, and then you can find any of these objects in the world in order log n time, right? So if you want to find out what this point is, you can do so in order log base 2n time, where n is the number of objects in the world. And so it's way faster. In video games, you need speed. You know, regular applications, I guess, too. So if you have 1 million objects, you can find anything in 20 steps rather than 1 million. Okay. Quiz question. Yeah, almost all, and when you're doing video games or graphics and things like that, almost every algorithm is going to be log n, you know. Or if you need to sort all the objects in the world, it'd be order n log n. That's kind of, you know, once you kind of get to that, you're like, all right, cool, I got a good algorithm. Okay. Like you know, make a fence that will surround these 4 objects, right? If you can do that in order n log n time, then you're good. Okay. So that's the kind of algorithms you do in computational geometry and video games and stuff like that. Okay, so let's come back in to our regular binary search tree. Nice detour, and let's talk about deleting. So there's a couple cases for deleting. What is the most? I think there's probably 5 different cases. Deleting. What different scenarios can you guys imagine when you're wanting to delete something from a binary search tree? Is the quad tree log base 4n? Yes. But again, the base of the log doesn't matter. Root, child, parent. What's the most basic thing? What is the most basic possibility if you're deleting from the pointer? I don't know what that means. What is the most basic scenario? Point to null. Yeah. So if the tree is empty, right? Empty tree. That's the mindset you need to get into when working with pointers, right? Don't assume the tree exists. If somebody calls delete on you, don't be like the standard librarian segfault. You know? Popping off an empty stack, segfault. Case 0, empty tree. Okay. Case 1, only the root exists. So, how do we code that? Become the tree, embrace the tree. So let's come up here and I don't know, just do delete, void, delete. We can't call it delete. Call it remove. Delete is a reserved keyword, right? See how it turns yellow? Don't name anything yellow. Don't eat yellow snow. All right, good life advice rather from 6th grade camp. All right, so if we want to remove something, const t reference key. So case 0. Tree is empty. If actually, I'm going to cheat a little bit. So if we say delete 15 from the tree, if we say delete 15 from the tree, and 15 is not in the tree, we don't have to do anything. You know what I mean? So I'm gonna start off by just cheating a little bit and saying if we cannot find the key, return. Right? Cool. See if it is in the tree before deleting it. This is going to double the running time of delete, but it'll make my code simpler to write, so I'm going to write it this way. I did the same thing for a linked list, if you remember. The good news is this is only an order login, usually, operation, so it's not too bad. So we're going to just see if, and if the tree, and this will handle the tree being empty, right? You know, this will handle empty tree. Okay, so now we know that there's a root. That's nice. So we can say, and we know that it's in the tree, so we don't have to worry about it not being in the tree. So we can say, is that a standard function? No, I wrote it. Remember that? Just did that a second ago. You get no standard library functions on your own data structures, right? D5D. Move it down here. Okay. So yeah, so I'm just gonna do that. Easy peasy. All right. So case 1, we need to see if we're deleting. Are we deleting the root? We'll need to handle that. Okay. In that case, the root is gonna change. In every other case, root's not going to change. We got a GIF loading over here. Yeah. The hell. Okay. So if we're deleting the root, and the root has no kids, then root's going to become null, right? Otherwise, root's going to change. Okay. So let's go over the other cases before we get into that. So case 2, we are deleting a node with no kids. AKA a leaf. Deleting a leaf is pretty easy. Let's draw this out for you. So if you're deleting, let's say you got 10, 5, and 16. So let's say you're deleting 16. All you have to do is delete it and set the parent's pointer to be null. 2 steps. Okay. So if you're deleting a leaf, there's 2 things. You delete that chunk of memory. You will say delete, that's current. You'll delete current points to right in this case, and then say current points to right equals null. That's it. So deleting the leaf node is pretty easy. Just deallocate it and set the pointer to it to be null. You're done. Oh my gosh, it's terrifying. People are posting trees with human faces on them. Okay. So what would that look like? Yeah, I don't know. You guys are worrying me a little bit. All right. So we'll handle worrying about the root later. So let's do this. node pointer current equals root. And then we're going to have a pointer to the parent as well. Okay. So as we go down the tree, what we're going to do is we're going to have, let's say that, we're going down the tree. We got parent, we got cur, and let's say we're going to delete this guy. Okay. So what's going to happen is the parent's pointer is going to move, and then some other stuff might happen down here as well. So as we iterate down the tree, parent is going to be always pointing at the person above current. Okay. All right. So okay. So we'll handle that later. Okay. So while true, if current points to data equals key, we have found the key. We probably could have the find function do this for us, or write a version of find so we don't have to repeat ourselves, but it's fine. So if we got a match, then we are going to end this loop. Otherwise, if the key is less than current points to data, we go to the left, right? So we're gonna go through the tree, and we're gonna set current equals current points to left, and we're gonna set parent equal to current. Otherwise, okay, so this code here is just going to find the current node. Okay, so we're doing a search. We're essentially doing the find function again, right? Do you guys see how this is the same code? Like I said, if I was a little more intelligent, I would have had find, or I could make a version of find that returns a pointer to the node and to the parent of the node. So what's going to happen here is that at the end of the day, we know we're going to find it. We know we're going to find it because I checked that it's in there. Okay. So what's going to happen is we're going to iterate down through this tree, and current is going to point to the person we're matching. If we're trying to delete 10, then current is going to be pointing at 10, and parent will be pointing at whatever the parent of 10 is, or whatever. Okay. -7. So at the end of this while loop, parent is going to be pointing at the parent of the person that's going to be deleted, and current is going to be the person that's going to be deleted. Okay. So, a couple different possibilities here. First is it's a leaf. So if case 1, leaf, case 2, one child, case 3, 2 children. So if the person we're going to delete is a leaf, if the person we're going to delete has one child, if the person we're going to delete has 2 children, we're going to have to handle that separately. Okay. So if we're deleting somebody that is a leaf node, so we've got 20, 40. Here's current. Here's parent. All we do is delete this and set the pointer to be null. That's it. 2 lines of code. So if it's a leaf, it's pretty easy. How do we tell if it's a leaf? If current points to left is null, and current points to right is null. So if both of the people that we're trying to delete has null pointers to either side, to left and right, then it's pretty easy to do. We simply say delete current, and we say parent points to. Ooh, yeah, we need to know which way. We need to know which way it went. Right is current the right child or the left child? Yeah. So if it was the left child of the parent, then they would say parent points to left equals null pointer. Otherwise, parent points to right equals null pointer. Okay. So this is just writing down, is it the left or the right child of the and there's a possible segfault here. Where is the possible segfault? It's only 3 lines of code, and 2 of them can segfault. How? What is that mindset you need to get into? Working with pointers. If else, where is the segfault? If an else doesn't cause the segfault, what's causing the segfault? Possibly. Delete current, but still calls for current in the conditional. Nope. It's not using the. It's checking to see if. Current's kids are both null, and then it deletes current. That's fine. Current cannot be null. It's started off as root, and it's going to move down to the left or to the right. Normally, current could become null, but we've checked to make sure it can't be. If current is in the tree, it'll never run off the bottom of the tree. It's going to hit at some point. It's going to find. Not deleting null. No, you can delete null, but current won't be null. If you delete null, it won't do anything. C++ ignores deleting a null. Check for null. Yeah, where? Who can be null? What is the risk factor here? What scenario will result in a segfault? Parent points to right being equal to null. That's fine. Null pointer is just 0, and so setting parent's right pointer to be equal to 0 is fine, right? That's not a segfault. Yeah, it's what we want. We want to set parent's right to be null, or left if it's the if current's the left child of it. Empty list. Empty list can't happen because we are only doing this code if we successfully found the element in it. What could cause a segfault here? Dereferencing a null pointer can cause a segfault. Assigning a null pointer, this does not cause a segfault. You can set something to null. That's fine. It's when you dereference a null, it's when you use the arrow operator. It's when you use the arrow operator and the pointer is 0, that is what segfaults you. Okay? If current equals parent, no, that's fine. Can't happen, but even if it was, that would it wouldn't be a segfault. It would be a use after free. Like if current and parent could somehow be the same, then it would be you would be deleting current and then using it after it was deleted, which is not necessarily a segfault. If you're deleting the root, correct. So if parent is null, so if you get a hit on the very first element in the tree, current's going to be set to root, and parent is not ever going to be set. And so if parent is still null, that means we're deleting the root. So we need to handle that. So if parent is still null, then we're just going to set root equal to null pointer and call it a day. So that handles that case that I was talking about, called deleting the root. Yep. So if you're deleting the root, then and if you're deleting the root and there are no kids, then that's the only time. Do you guys remember that class invariant? Root points at the top of the tree. If the tree is empty, it points at null. So the only time you can have an empty tree is when there's exactly one element in the tree. Both of its kids are null. One element. We delete it. That's the only case where we need to do this. That handles the class invariant. So if we're deleting the very last element of the tree, then root needs to be set back to null. You mentioned deleting null in C++ is ignored. You can do it for sanity check, sure. If not null, delete. It's fine. Why not? I usually write code like that. This makes me feel nervous. Yeah. So I'll write like if left, delete left, right? You can do that if you like. You don't need to, but you can. All right. Deleting null is ignored. And I seem to recall that not always being true also. Kind of changed at some point. So if you're using older C++, yeah, probably want to use the if statement. Okay, so we got, 4 minutes left, so we're not going to get through this today. So good news, you guys aren't going to have your next homework assignment yet. That'll be given to you guys on Wednesday. Okay, we don't have time to get through this quite today and go through a new homework assignment. So yeah, enjoy your day off. Start doing the Zybooks. Please read the Zybooks. Actually, it's probably a good idea to do the Zybooks as quickly as possible because it's on binary trees. And again, you have to understand conceptually what's happening, and you have to understand the code and the pitfalls, and you have to understand how to debug stuff when it doesn't work right. Binary trees and linked lists are the two big brain melters this class. Stacks, queues, vectors are easy to get. The proper class design, you just need to work with it a little bit. It's not bad overall. Zybooks is great. Make sure you guys do it. Yeah. So, okay. So let's do one more case, which is when there's one child. Okay. So if you're going to delete a parent with one child, then, by the way, FBI, if you're listening, we're talking about programming, not actual parents and children. Okay. So 20 points to 30 points to 25. Okay. So this is a case where a parent with one child. Step 1, fork parent, kill child. Okay. So if we're going to delete 30, let's say. So that's the current, and this is parent. What do? How do we, what pointers need to be cleaned up here? What do we need to do if we're going to delete 30? And remember, 30 could have either a left child or it could have a right child. We don't know. We don't know which yet. If you get your grade for bridges earthquakes first, yeah, I'm working on it. I'm working on it. I'm trying to get the competency exams done first because those are the most important for you guys. So, what do we do? What pointer needs to be cleaned up? Being a parent sounds weird. No, it's fun, dude. If you've ever had a pet, like a dog or a cat or a pig or something, that's all that being a parent's like. Current's here. Delete that. Child labor. No, come on, dude. Child labor is wrong. I only make my daughter like plant my turnips and carrots in video games, not real life. Ada, go tend to the bees, collect the honey. I need to make mead. So yeah, so we need to make the parent point to this guy here. Okay, so what we need to do is have the right pointer of parent point to the child. So that's what we need to do. We need to set parents right, equal occurrence left. Okay. Go mine some diamonds for me. FBI in a video game. It's okay. So, else if current points to left, so that means that current has a left child. So we're going to say delete, let's see, parent points to, if it's our left kid, then parent points to left equals, parent points to left equals current points to left, else parent points to right equals current points to left. So one child and is the left child. Okay, and then we also need to check for root. We do check for root. And then we will delete current. Two, three, four, five, six. Else if it's a one child, let's see. Oh shoot, we have to do this one first actually. There, it is. So if we have a left, so if the one we're deleting has a left child but not a right child, then we set parent's pointer to be the left child. If we have a right child but not a left child, we set the parent's pointer to be the opposite. And then finally, there is the case of two children, and that we will talk about next time. That's the hardest one. So what we're doing here, and that probably caused you to go cross-eyed maybe. If you've got a parent, if we delete him, then we have to do that. If it looks like this, we do that. If it looks like this, we do that. Okay, so there's four possibilities, right? And these are the four possibilities here. Okay. And then we will currently seg fault because we're not checking to see if we're on the root right now. So, and then the big complex thing is deleting when there's two kids. So that gets complicated. You know, you're having a divorce. What happens? The two kids. Father gets one. Mother gets one. I'm kidding. It's not divorce. It's murder here. the parent is killing the child who themselves is child. So it's a grandparent killing a parent. Again, FBI, don't come after me. Parents killing there's 2 grandkids. What do you do with them? Solomon, yeah. Got to Solomon the babies. All right, so that's it for today, guys. Just all conceptual stuff today. No homework other than your Zybooks, but really do the Zybooks for the binary search trees. Get cracking on that. And if you can understand conceptually what's happening, you're going to write good code. If you don't understand conceptually what's happening, your code is going to be garbage. It will be absolute garbage, and it won't work. So, okay. So we're going to keep hitting this until we get it. All right. Be on the lookout for the next competency exams. If you didn't pass the class ones, make an appointment with Muya, and he will give you the password for part 4 whenever that goes live. All right. Peace out, you guys.